Assalamu alaikum, my name is Najaf and my roll number is 21TE06. Today I will be discussing lab number 8 of digital signal processing, and the title of the lab is Moving Average Filter, FIR Filter, Fourier Transform Design Method. Lab objectives are implementation and analysis of moving average filter, implementation and analysis of finite impulse response filter Fourier Transform Design Method. Task 1. Part A, define filter. Part B, types of filter. Part C, what are the time domain parameters for a filter? Part D, what are the frequency domain parameters for a filter? Part E, discuss the role of low pass filter for filtering design. Answer for part A is, a filter is an electronic circuit or algorithm that allows certain frequencies to pass through while attenuating others. In simple words, it's a device that modifies the amplitude or phase of a signal based on its frequency content. Part B is about types of filters. The filters can be categorized based on their frequency response characteristic. Some common types include low pass filter. A low pass filter allows frequencies below a certain cutoff frequency to pass through. And here is the circuit diagram of low pass filter. High pass filter. High pass filter allows frequencies above a certain cutoff frequency to pass through. Band pass filter. Band pass filter allows a specific range of frequencies termed the pass band to pass through. The type 4 is band stop filter, also known as a notch filter. It attenuates a specific range of frequencies termed the stop band while allowing others to pass. Part C is about time domain parameters for a filter. In the time domain, filters are characterized by parameters such as impulse response, step response, rise time, and settling time. The impulse response describes the filter's output when an impulse is applied at the output. The step response describes the filter output when a step function is applied at the input. The rise time is the time that it takes for the filter's output to rise from a specific low value to a specified high value when a step function is applied. The fourth one is settling time. Settling time is the time it takes for the filter's output to reach and remain within a specified range of its final value after a step input. Part D is about frequency domain parameters for a filter. There are 4 parameters for the frequency domain: frequency response, cutoff frequency, bandwidth, and stop band. Frequency response describes how the filter affects different frequencies in the input signal, and it is typically represented by a magnitude and phase response. The cutoff frequency is the frequency at which the filter's response is attenuated by a certain amount, often 3 dB for practical purposes. For example, in a low-pass filter, it is a frequency where the filter starts attenuating. Third one is the bandwidth. Bandwidth is the range of frequencies that the filter allows to pass through relatively unattenuated. The fourth one is stop band, and stop band is the range of frequencies in which the filter attenuates the signal significantly. Part E is about the role of low-pass filter in filter designing. A low-pass filter is essential in filter design for several reasons. The first one is noise reduction. In many practical applications, signals may contain high-frequency noise that can distort or interfere with the desired signal. A low-pass filter can attenuate this noise while preserving the lower frequency components of the signal. The second one is anti-aliasing. In digital signal processing, before analog signals are converted into digital form, which is sampling, high-frequency components above the Nyquist frequency can cause aliasing, resulting in distortion. A low-pass filter is often used before sampling to remove these high-frequency components, ensuring accurate digitization. Signal conditioning. Low-pass filters are also used to condition signals by removing unwanted high-frequency components, smoothing signals, and reducing jitter or rapid fluctuations, making them more suitable for subsequent processing or analysis. Task number 2. Plot the signal in time and frequency domain along with its magnitude response. Part B is apply 3 taps symmetrically around moving average filter on signal X noise and observe the time and frequency domain parameters. Part C is apply 11 taps symmetrically around moving average filter on signal X noise and observe the time and frequency domain parameters. Part D is apply 25 taps symmetrically around moving average filter on signal X noise and observe the time and frequency domain parameters. Symmetrically around moving average filter is given by this. you may use frequency function to observe frequency domain parameters. Now, explaining its MATLAB code, we created an ideal signal, which is essentially a pulse signal, which is composed of zeros except for central portion where it is 1. To simulate it in the real world scenarios, we added noise to the ideal signal, and the actual signal is generated by adding random noise to the ideal signal. Here, the fast Fourier transform of the actual signal is computed to analyze its frequency content. In the first subplot, we observe the actual signal in the figure. Here, moving average filter is implemented as a simple low-pass filter, and it is designed with a specific number of taps. The filter coefficients are computed such that each coefficient is divided by 1, is 1 divided by the number of taps, essentially creating an averaging effect. The convolution function is used to convolve the actual signal with the filter coefficients, resulting in a filtered signal. Now, if we observe its output, in the first figure, the actual signal is displayed, and in the second figure, we observe that the filtered signal is displayed along the original signal. It is the before filter, and this one is the after filter. Task number 3. Repeat example 7.2 with 7 tap, 17 tap, 51 tap, and 101 tap. Observe the frequency domain parameters. Calculate first filter coefficients for the 3 tap number FIR low pass filter with a cutoff frequency of 800 Hz and a sampling rate of 8000 Hz using the Fourier transform method. Determine the transfer function and difference equation for the design FIR filter system. Compute and plot the magnitude frequency response for omega 0, pi by 4, pi by 2, 3, pi by 4, and pi. Part B is about applying the filters made in part A to the signal X signal. Observe the changes for signal X in the time and frequency domain while varying the number of coefficients for the filter. And here are the given specifications. Here in the MATLAB code, taps is the number of the filter taps, FC is the cutoff frequency of the filter, and Fs is the sampling frequency. For FIR filter design, we used FIR 1 function to design a FIR filter with taps 1 order and a normalized cutoff frequency with the name normalized cutoff. Then for displaying the filter coefficients, we design FIR filter for the coefficients of the design FIR filter are displayed using the Dsp function. The transfer function of the filter is in the Z domain is computed and simplified. Then the difference equation representing the filter is formulated and displayed. For the frequency response of the filter is computed using the frequency function over the frequency range from 0 to pi. Now, when we run this code, we will observe in the command window the filter coefficients are displayed, then the transfer function is displayed, and thirdly, the difference equation is displayed. Here, we see that the frequency is in the axis and magnitude is labeled in the y-axis. Here we see that the plotted frequency response allows for visualizing how the filter attenuates or passes certain frequency components, while the specific frequency points help us in understanding the filter's behavior at key frequencies. Here in the part C of task number 3, we designed a filter with 51 taps. The rest is same, whereas in signal generation, three sinusoid signals of different frequencies are generated and added together to form a composite signal, signal X. And then for the filtering, we designed the FIR filter where H, and it is convolved with the composite signal X using the convolution function to obtain the filtered signal. For the frequency analysis, we um, use the Fourier transform, the fast Fourier transform of the filtered signal uh, to analyze its frequency content, and then we plot the magnitude spectrum of the filtered signal. Now, if we run this code, here in this figure, the first subplot is about the signal X, which is the addition of all the three sinusoidal signals, and the second subplot is of the filtered signal, and the third subplot is of the frequencies of the filtered signal. Number 4 is the part 1. The part A is repeat example 7.3 with 7 tab, 17 tab, 51 tab, and 101 tab. Observe the frequency domain parameters. The example is firstly calculate the filter coefficients for a 5-tab filter, FIR bandpass filter with a lower cutoff frequency of 2000 Hz and an upper cutoff frequency of 24,000 Hz with a sampling rate of 8000 Hz. Part B is determine the transfer function and plot the frequency response in MATLAB. We've been given the following specifications, and part B is about applying the filters made in the part A to the signal X signal and observe the changes for signal X in time and frequency domain while varying the number of coefficients of the filter. Now, solving the example 7.3 for a 17 tab filter, we observe that low FC is 2000, whereas high FC is 24,000. Fs is the sampling frequency, and Nyquist is the Nyquist frequency, which is half of the sampling frequency. For the normalization of the cutoff frequency, the cutoff frequencies are normalized by dividing them by the Nyquist frequency. Thirdly, for the FIR filter design, the FIR1 function is used to design an FIR bandpass filter with tabs -1 order and normalized cutoff frequencies specified as low NC and high NC. For displaying the filter coefficients, we use the display function. For displaying for the transfer function, for the transfer function of the filter in the Z domain is computed and simplified. Now for the frequency response is computed using the frequency function over the frequency range from 0 to pi, and then the magnitude response is plotted against the frequency. Now if we run the code in the command window, we will observe the filter coefficients and then the transfer function of the filter. And in the figure number 1, we observe the magnitude response, which is plotted against the frequency. And the plotted frequency response allows us to visualize how the filter attenuates or passes certain frequency components within a specified bandpass range. Now, performing the last part of lab number 8, task 4, we designed a filter with 51 tabs, whereas low FC is 2000, high FC is 24,000, and the sampling frequency is 8000, whereas Nyquist frequency is the half of the sampling frequency. Here in signal X is added together of the signal X is the addition of the three different sinusoidal signals of different frequency, and then they are added together to form a composite signal, which is represented by signal X. And then for the normalization of the cutoff frequency, we divide these frequencies by the Nyquist frequency, which is here. For the design of the FIR filter, we use the function FIR1, and it is used to design an FIR bandpass filter with the tabs -1 order, and the normalized cutoff frequency is specified by the low NC and high NC. For the filtering, we design an FIR filter H, and it is convolved with the composite signal X using the convolve function, and it is the convolution of the function is to obtain the filtered signal. Then for the plotting, the subplots are used to display the original signal and the filtered signal and the frequency content of the filtered signal. So when we run the code, in the figure 1, we observe that the first subplot is of signal X, which is the added signal of all the three different sinusoidal signal with different frequencies. The second subplot is the filtered signal, and the third subplot is the frequency content of the filtered signal. That's it from lab number 8. We'll see you in the next video. Thank you.